So, in the past few sections, we learned about we learned how to estimate, distances, areas, and so on, using sums. So basically, we first drew a series of rectangles under the curve. Then we drew a series of trapezoids under the curve, and we added up all of those areas of, each of the rectangles and each of the trapezoids. Now, as much as we said that we have an we have, a large number of rectangles and a large number of, trapezoids, right? What we were doing was still a finite number, right? Like we were doing like 10, 20, 5 subintervals, okay? Yeah. And we said that the approximation gets more and more accurate as the number of rectangles or the trapezoids increases to infinity. So what we were doing right now was still finite sums, right? We were doing finite sums, and then today we're going to move away from finite sums to infinite sums. We're going to see what happens if you, just a sec. We're going to see what happens if the number of triangles or the number of rectangles is now infinitely large. Yeah.
So why would you ever do finite sums? Because there's so much.
Right, there is a lot of room for error, right?
So
yeah.
Why would you do finite sums and trying to solve this?
It's an approximation. Yeah, that's what. Yeah, it's an approximation. So in math, there are always, in calculus especially, and I've mentioned this, a couple times last year as well. There are always 3 ways to solve something. One is graphically, one is analytically, and one is numerically. And numerically, the numerical way of solving things is just like ad nauseum, plugging in like a number after another, after another, after another, and then getting close to an approximation, right? And so it's sometimes it's close enough, it's good enough, and then other times not. Okay, so if what we were doing before, right, was adding up all of the areas, right, then we can write it in sigma notation like this, right? A1 plus A2 plus A3 all the way to AN. These are the areas of the individual rectangles, and we added them all up. And I can write it in sigma notation, and it looks like this. So this is the summation. This is adding up all of the individual areas, from 1 to n infinity. The sigma notation is, but not the areas. Okay, so this process is called taking Riemann sums, named after the mathematician by the name of Riemann. So LRAM, MRAM, these are all examples of Riemann sums. Okay, now let's talk about integrals. All continuous functions are integrable. This is the same as something being differentiable, but integrable, right? That means you can take an integral over it. Okay, so all continuous functions are integrable, which means on an interval a to b, the definite integral will exist. Okay, what is a definite integral? Fine, all continuous functions are able to, have a definite integral. But what is a definite integral? What it is this. Let's define it. The definite integral of a continuous function on the interval a, b. Okay, if f is continuous from a to b, okay, and if we partition a to b into n subintervals, just like we were doing, of equal length, then what is the length of each subinterval, or what is the width of each subinterval? It's b minus a over n, right? Remember, that's the width of each subinterval. We're going to call that delta x. So delta x, if I have my subintervals, is this. Okay, now, So how are we finding the area then? It was adding up all of the individual areas. So in this case, for that particular rectangle, the area is delta x times f of x evaluated at C. So if this is the point C, then this is f of C. Is that right? So the area of that one rectangle is delta x times f of C. What's the area of the next rectangle?
Delta x times f of c plus 1.
So delta x,
But they're not rectangles. So
well, they are now. Like if I close them off, they are, right?
oh, so this is not like trapezoidal.
No, I'm just doing like a rectangle. It does, yeah, I'm doing a rectangle right now. Yeah, not trapezoidal, RRAM or LRAM, okay?
Those aren't Riemann sums.
They are. LRAM and RRAM are Riemann sums. I'm just going over them
It's
again.
like T-RAM. Like, is that a Riemann sum?
No. Okay, so if that was C, suppose this is like, C1, so now this is going to be F of C1, and so on, right? So the total area is delta x times F of C plus delta x times F of C1, and then if there were more, delta x times F of C2, delta x times F of C3, all the way to N. So I can list them like this, plus, 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 or I could write it as a summation, like this. So let's ignore the limit for a minute. How do I write the summation? It's delta x times f of c, and then I add them all up from 1 to n. Okay? So what this is delta x is the base, f of c is the height. So if I generate the terms here, it'll be delta x times f of c1 plus delta x times f of c2 plus delta x times f of c3, and so on.
This is just a different format of writing.
Right, it's just a different way of writing it. But now, how are we going to make this to be the most accurate? It's when n, the number of subintervals, approaches infinity. Okay? So now,
Oh, okay.
yeah, I'm not going to keep it a secret. Okay. Okay. So that's what a definite integral is. It's basically adding up all the sums, but with infinite number of rectangles. Okay. So now you see what it looks like. It's very important to me that you understand why it's f of c times delta x. Do we all understand that? Okay. Now, if I have two subintervals, look at how big delta x is. Now, as I move to an infinite number of subintervals, delta x will become very, very tiny, right? That width will become very, very tiny. Okay, so now here is the notation introduced by Leibniz. This is the integral from A to B. That same thing that we just talked about, but now in the form of an integral. Okay, so look at what this looks like. Look at what you have here. You have f of x times dx. Guess what dx is? Dx is delta x when the delta x is super, super tiny. So it's delta x for normal lengths, like a millimeter, 0.001 of a millimeter. And then if it's infinitesimally small, it's dx. Okay? So dx is the same as delta x. So that's the base. This is the height of the function. Now, the sigma becomes this symbol, which we call an integral sign. So now, if in Greek, sigma is the Greek letter that makes the s sound, that's like an S. So this is like a squished S for sum. Okay? So the sum, okay, of f of x times dx from where to where? From A to B. A to B is called the limits of integration. A is the lower limit of integration. B is the upper limit of integration. Now, the function, right, f of x that goes in there is called an integrand. Just like the stuff underneath the radical is called the radicand, this is the integrand. So an example of an integral, let's say, will look like, negative 1 to 4 x squared minus x dx. Okay? Integrand, limits of integration, integral sign, and then that's the dx. Okay? Okay. Questions? Okay, let's move on to some integrals then. Here, each c is chosen from the kth subinterval of a regular partition of the indicated intervals into n subintervals of length delta x. Estimate the limit as a definite integral. Okay, what this is if you had, this is telling you, like, they're taking a sample and then adding them all up. So basically what you have to do is you have to write this as an integral. All right, so what are the limits of integration here? From where to where does this run? It goes from -7 to 5. Okay, and what are we integrating? So look at what we have here. We have this sum, which we write as an integral. It's like a squished s. What is it that we are integrating in here? This is the function. So this is a constant substituted into the function. So this translates, the original function would have been x squared minus 3x, and then somebody substituted the value of c in there. Okay, so this is x squared minus 3x. They're taking it here like some random strip where it's evaluated at c. Okay, c is a random point on the, it's a random x value. So when you plug in the value of c, the x value of c, into the function, you get c squared minus 3c. Well, what was the original function? X squared minus 3x. Delta x translates to dx, and this goes from -7 to 5. Okay? That's all we're doing here. Okay?
Do we have to write, like, because it has like the k equals 1 and then like, where does that?
All of this, the limit and the sigma, all right, is now, it's the integral symbol. It gets replaced by the integral symbol.
So how do you know, like the k equals 1, like how do you know, what if it was like 2, how would you know?
It's not, that's the thing. What this says is divide. It's never going to start from 2. What this says is you have the region from -7 to 5, divide it into n subintervals, and then add them all up. It's never it's not a partial sum, it's a full sum.
So dx is the distance between each subinterval, correct?
Correct.
So like if there was like if you were going from -7 to 5 over 4 subintervals, dx would be 3, right?
No, dx wouldn't exist then, because if you have 4 subintervals, dx is an infinitesimal amount of space. It only exists when it's an infinite number of subintervals.
So
okay.
If you're not doing the whole infinity
right
type of thing, there won't be a dx.
Correct. Now, I have to say more about the dx, but bear with me for a minute. So here again, this whole thing is just integral. And then here, my function used to be 1 over 1 minus x before I substituted c values in there. Dx from 2 to 3. Okay? And it's, You'll figure out when to put the parentheses and when to not, but let's put it in for now. Okay, now, area under a curve. So if f of x is a non-negative, meaning 0 or positive, and integrable function over a closed interval AB, then the area under the curve is just this, which we already knew, right? That's the area under a curve. So if I ask you to find the area under a curve, that's what it is. If I was walking down the street and I just saw, without the a, integral a to b f of x dx, I will think to myself, somebody's looking for the area under f of x from a to b. Okay? That's what that is. Okay. So take a look here for a minute. Quickly. We have a function f of x is the root of 4 minus x squared. What shape is that going to look like? Semicircle with a radius of 2. So you have to know this. Okay, you have to know this. So what this is telling me is find the area under this curve. So basically, I need to find the area under this curve. And you know what? We're going to use geometry formulas from middle school. This is the area of a semicircle. You know what? I know how to find the area of a semicircle. It's half pi times the radius 2 squared. And that's it. It's 2 pi. These are freebie points. Okay? All right. Take a look at this one. My function is negative 2x plus 4. Let's graph it. Y-intercept is 4. And when y is 0, x is 2. Okay, so we're going to graph y equals negative 2x plus 4. And it's going to look like this. But right? You can go further than the x-axis, that's fine, or you could just stop, that's fine too, because we're only going from x equals 0 to 2. And now I need to find the area of this cute little triangle. So area is half times the base, 2 times the height, 4, so it's just 4. So again, when we say curve, it doesn't have to look a certain way. Any graph of a function is a curve. Yeah. I know in the real world, curve means like, curvy. But in math, curve is just the graph of any function. Y equals 3 is also a curve. Okay? Straight line. Yep. We don't discriminate here. Okay, now, so we said before, and I stressed the term non-negative, 0 or positive. And you see here, both of these curves are positive, right? They're above the x-axis. So what happens when a graph goes below the x-axis? This is like one of those dun-dun-dun situations, right? So look at this one. I have from negative 3 to 3, mistake. There should be a negative here. That's how you graph the negative. Okay? There should be a negative here in order, yeah, there's a typo. Put a negative in there in order for it to graph this. Now, the area, right? What this does is, because it's underneath the x-axis, the area will become negative. Okay? Think about this. In geometry, we always told you, but area has to be positive. But this is not the area of a geometric shape. This is not the area that you're trying to paint or something, right? If area under a curve can represent velocity, can velocity be negative? Yeah. Can displacement be negative? Yeah. So under the curve, velocity is negative. These go together. Okay? So you just put a negative in front of the whole radical. Okay, I'm sorry, not radical, integral. So this is going to be negative 1/2 pi 3 squared. Okay, so you find the area of a semicircle just like you would, but then you put a negative out front. And so this is negative 9 pi over 2. Okay. Now, we did the case when you have a graph above the x-axis. We did the case when you have a graph strictly below the y-axis. But what if some of it is above and some of it is below? Then what you do is you find the area of the portion above the x-axis and you subtract the area which is below the x-axis. Okay, so find all the areas, but the ones in the bottom are negative, negative, negative. So look at this. It says evaluate the integral of blah, 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 blah using area. So basically, I just have to find the area between the curve and the x-axis of this. That's what that funny little, group of symbols means. So just find this area. Okay, so let's do it. Let's find the area. Here I have a triangle, the height of which is 1. So the area here is half times the base, which is 4, times 1. I don't care that the x values are negative. All I care is that the y values are positive. So this is a 2. Here, this is a lovely trapezoid, and now we know how to find the area of a trapezoid. Area is h over 2. What's the height here? 3. Base 1, 4, plus base 2, 2. Man, do I love math. Don't you guys love math? It's 9. 3 over 2, 4 plus 2. Count. 2. Okay, so the area then, negative 4 to 4. Okay, sorry. Notation. Notation. Don't say area. The integral from negative 4 to 4 f of x dx, because that means area. Okay, equals 2 minus 9, negative 7. Okay. Yes, you can have negative area because we now know, right? Area stands for other things, other values, quantities. Okay. So then what's the integral of a constant, right? What if f of x is a constant? C, y equals 3, our favorite constant function. Then take a look at what it looks like, right? So if I have f of x equals c, it's that horizontal line. And if I'm looking for the integral from a to b, then I have, a straight out rectangle, right? So how do I find the area of that? It's just this c, right, times this b minus a. We don't even need calculus for that. Okay? So if I have the integral of f of x dx, then it's just c times b minus a. And if it happens to be underneath the y-axis or the x-axis, then it's just the negative of it. So remember we did this in section 1, the train that was going at a steady rate of 75 miles an hour? Remember? Let's go back to that train that's going with a steady rate of 75 miles per hour from 7 to 9, right? Do you remember we drew the rectangle, we did this, we did that? Now, when we're asked for the total distance, we say, oh, that's the integral of this function, which is 75. Okay. We're going from 7 to 9, correct? Don't go from 0 to 2. We're going from 7 to 9. Now, this is supposed to be dx. It's supposed to be d, the independent variable. What's the independent variable now? T, right? That horizontal axis is t. So now it's dt. Okay? Now, are we integrating a constant? Is this the integral of a constant function? It is. then it's just 75 times 9 minus 7. 150 miles. Let's do the unit analysis one more time, the dimensional analysis one more time. 75 was miles per hour. I multiplied it by delta T, hour. Miles per hour times hour is miles. So remember what got you here. I always say, remember the little people that got you somewhere. Remember what got us here. It was area. This was dx, or this was delta x. It's still delta t. So this is time, this is miles per hour. Okay. So let's evaluate these very quickly. We have a constant. So it's -6. I'll do it here. -6 times 7 minus 3. That's -24. Oh my, I have a pi and stuff. That's fine, because that's still a constant. -1 minus -4. Does the direction matter there? Yes, of course it matters, because these are like vector quantities, right? Velocity, displacement. Okay? So the sign matters. 3 pi over 2. Isn't math fun? This is like some of my favorite stuff. Like there's a whole world, like a whole secret world you guys are being led into. Like this is like super cool stuff. Okay. Okay. So, how are you guys doing? Are we going too fast, too slow, just right?
Just right.
Okay. All right. Use the graph of the integrand. Where is the integrand? Right? So -2x plus 4 in this case, right? And the area is to evaluate each integral. Because what is an integral? Just area. Okay? So, -2x plus 4, what are we going to do? We're going to graph it. So, when x is 0, y is 4. When y is 0, x is 2. We did this before, right? But we now have different limits of integration. Okay. But now, all right, you know what? I didn't do this right. Okay. It passes through here, right? That's important. Okay. We're going to go from 0 to 1. So here. All right, so this is what I want. Okay, that's a trapezoid. So it's important now, right, for you to know how to evaluate that point when x is 1, y is 2. Okay? You can either plug it in, you can do whatever you want. Oh, no. Not ignore it. All right, so what's the trapezoid there? It's what? 1 over 2. 1 over 2. Okay.
4 plus 2.
Yep. And so that's 3. Okay, and now what's that going to look like? That way or that way? It's going to be... It's going to go down, right? Yeah. So when x is 0, y is 1, and then what are the x-intercepts? 1 and -1. Okay. Now, when you find area under a curve, that's okay. When you find the area, it's the area between the curve and the x-axis. The curve and the x-axis. So when we're going from -2 to 2, yeah. In here, this is the region between the curve and the x-axis. Here, it's this and then this, right? There is no middle because it's between the x-axis and the curve. Yep.
If you're doing it like
I love this problem.
well, if you're doing it like this with dx, so if you're what happens if it's not like the shape of the triangle or the trapezoid that says one figures, they put the curve, they don't have a specific formula to find it. How would you?
You will always have a specific formula. That's the thing. You will always have a function.
There's no have shapes and up there like I forget what's called with the shapes. So.
That's all in second half of this chapter. Yep. Okay, so tell me. Yep. It's 0. The area is 0. Why? Because look at this. Each one of these little triangles has a -1 underneath. Do you see that? So positive area, negative area, positive area, negative area of equal length, or of equal area, right? Of equal magnitude. So the area here is 0. Yes. It is very nice. Right? So if we're talking about distance or displacement, is it possible to start from a point, right? If this integral represented our displacement, is it possible to start from a point, walk, and then keep walking, and then you end up at the same point, so your displacement is 0? Of course, right? There is a lot of action that happened, but your displacement is 0. Okay, this one's important. Find points of discontinuity of the integrand on the interval of integration and use the area to evaluate the integral. Okay, absolute value of integrals of absolute values are very, very important. When you have integral and absolute value together, you have to think about separating them, okay? So take a look at this one. I have x over x. Last one. Okay, so I have x over x. If x was 1, what would I get here? What would y be? 1. What if x was 50? 1. What if x was 70? 1. So it's like 1, 1, 1, 1, 1. Okay, here, 1. What if x was -1? Now this would be negative, right? What if x was -2? -2, and so on. And so here it's this. At x equals 0, what is it? 0 over 0. Does it exist? No. So open circle, open circle. You have got to be able to reproduce this because they can ask you this question. They can ask you about like the limit here, the y value there. I mean, you need to know how to do stuff like this, okay? Figure things out, reason them out, okay? So here, our y is x over x, meaning there is a point of discontinuity at x equals 0, and it's a jump discontinuity, right? So we'll learn later that whenever you have an absolute value, that's technically a piecewise function. That's why you get a jump discontinuity there. Okay, so now if I want the integral from -1 to 2, it doesn't matter that there is an open circle there. I can still find the area there is 1, and the area here is 2. So what do I write here? 2 minus 1. Equals 1. Okay? Okay. So, let's do this with the calculator. Go ahead and take out your calculators, please. We have to find the area under the curve y equals root x from 0 to 4. We should be able to graph this without a calculator, right? So, at x equals 0, it's 0. At 1, it's 1, and then at 4, it's 2. So basically, this looks like this, and I want the, area of that region, okay? Now, so using the graph, plug in the function into F1, so go into graphs, and then plug in the function, the square root of x, Where's my calculator here? Okay, so the square root of x, right? That's what it looks like. And then you're going to go to menu, analyze graph, and you're going to do integral. And maybe I want to make this bigger. Okay, here it asks you for a lower bound. You can either scroll it over to to 0 and press enter, right here, 0 and press or click. And then now you want upper bound. You can either bring it to the point, or you can just go and type in the upper bound 4. Oh no, that's the lower bound. So I want lower bound 0, enter. Oh no. All right, let's do it again. Menu, analyze graph, integral. With my mouse, it's giving me, okay, so I know my mouse, it gets tricky with the mouse. So I'll do it without the mouse. So lower bound, I'm going to go 0, enter. Upper bound, I'm going to go 4, enter. There it is. It's 5.33333. It highlights the region for you. It gives you the region. It gives you the area. And that's what it is. Huh? Did you do 0 and 4 or 4 and 0? I'll take a look right now. Let's do it using the home screen, right? So using the home screen, you're going to go to menu. Calculus is number 4. And remember how before we did numerical derivative? Now we're going to do numerical integral. That's the second one down. And then it just gives you this cute little, wonderful interface. And you just put in here 0 to 4. You can keep pressing tab to go from one to the other. That's the easiest thing. And then root x. One day I'll bring the calculators I used to use. It's interesting, yes. Dx. And then you just press enter. And look, you get the same answer. Did everybody get 5.33333?
Yeah.
Okay? Okay. What I want you to do now, while I'm checking their calculators, I want you to do these two, but, okay, I'm so excited. I keep yelling and now I'm not going to be able to talk the rest of the day. Okay. I want you to do these two here. For this one, your calculator has to be in radian.
That's why I just got it.
Yup. Okay, go ahead and do these two. Don't call out the answer. Just sit tight. Write it down. Sit tight. Okay, so let's go. Let me do this one. I'm going to do it. Shh. Okay, my turn now. I'm going to do B. 4 over 1 plus x squared. That's what that looks like. And we're going to go from 0 to 1, right? So I'm going to go to menu, analyze graph, integral from 0 to 1. Is that 1? One. Look at what is that number? Pi. You get pi. 3.14159. Isn't that cool? So this one, I'll tell you. This one, oh my gosh. I can't write. It's not letting me write. Oh my gosh, why can't I? So 3.142 or pi. Again, if this is on like a multiple choice and like, and if the answer choices are pi, e over 2, whatever, you should be able to recognize, what it is. What did we get for this one?
2.043.
2.043. Okay, I have a couple of things to say before I answer any more questions. So this homework will be due next week, Tuesday, right? So a week from today. And then if you go on my jug, you will see that I have the schedule up. There is a quiz next Thursday, all right, on this stuff. Now,